thank the advisors thank the organizers for inviting me to this meeting. And it is appropriately named Less Traveled, a path. If they have kept any prize for the least traveled, I would get it because only 3 people have so far traveled this path. So I will try to motivate and explain what is meant by this fact. So, I mean, the word emergent refers to the fact that it's not really simply some chunk of energy lying there or cosmological constant, but there is actually a physics that reasonably familiar to us, which underlies, which comes together to mimic the dark energy. So we will go over just some introduction, and then I will try to cover some of the existing experimental indicators we have as to where we should be looking. These are really the broadest scale experiments and analyses. And just to motivate the kind of path we have taken, I will just explain one of the classes of models that looks at this. There are, of course, a large number of models. And finally, I'll come to this hidden U1X, a hidden quantum electrodynamics along with electrons and hidden protons, which should work as, which should simulate somehow the dark energy. And as plus points, it is interesting that it is possible to fit even dark matter into the same model, not compulsively, but in a very convenient way without having to struggle over the mass scales. And finally, it also turns out, because our model relies strongly on a magnetic field idea, ferromagnetism, that the model may also explain origin of cosmic magnetic fields. So now what happens? Yes, okay. So the dilemmas in a nutshell, written for very elementary explanation, of course, are that we have the two Einstein equations, in which this is the famous constant that Einstein introduced, of course, with opposite sign. But if you transfer it to the right-hand side, then you can always make it look like dark energy. So, I mean, what we call dark energy now is best parameterized by the CMB people as just a cosmological constant. And then we have this fact that there is a distribution between of how much dark matter there is, how much dark energy there is. And of course, it's a great puzzle that these are numbers that are extremely small. For example, the dark energy, if you think of it as some sort of vacuum energy, is much, much smaller than the standard model HEP scale. And also, there seems to be some relation between the dark energy and dark matter because they are within, a fraction of each other. So it is interesting then to think of a sector that autonomously operates independent of anything we know and trying to connect to anything we know directly. First, come up with a model and then try to see if it connects to the standard model. Now, let me see so the dark energy, I think I've just summarized here why we believe in dark energy, which has to do primarily with the new standard candles that we acquired, which involve this type 1a supernovae. And I really written this down that for Indian audience, it is interesting to know that why this type 1a supernovae can be used as standard candles has to do with the fact that the white dwarf mass is limited by Chandrasekhar limit of 1.4 solar masses. And therefore, in all those binaries, the masses are fairly standardized. And therefore, the signal becomes very standard. So it's a very important thing that these limits have placed. And this number is old because it's about double by now. More than 1,000 such sources have been done. So this is just to put in perspective the immense amount of length scales that we go through and also the different methods that are followed. Local, of course, parallax. Everything is going by orders, numbers of zeros. And sometimes we forget what a huge time scale it is and how tenuous the dark energy that we are trying to search for. So this is how it goes. And let me then summarize what is the current situation with respect to understanding of dark energy. Lambda CDM, of course, says that it is a constant lambda, and which quote a number for it, which fits well everything. But there are these observational projects which have all come together, which I will not be able to go into, and they call themselves pantheon, as you know, as in many different religious beliefs coming together to express the same truths or something like that. This is Pantheon Plus now, which came out last year, but as I could check, it is even updated November 22. What they try to do is parameterize P equal to W rho. In the lambda CDM, W is exactly -1, but you could parameterize W as a function of redshift by a W0 and by a WA, which is like the first derivative, but with this kind of proportionality to Z. And then there are three classes of models. The flat lambda CDM, of course, is the standard one. The CMB one. But then you could consider this so-called flat omega CDM, where this parameter is readjusted to match the data, but the omega A is kept strictly 0. And then you can also, and flat just means that we are going to keep K always equal to 0. And then a third class of models they consider are where both omega 0 and omega A are allowed to vary. And this is their constraint for.
So then omega 0 varies with Z?
No, omega 0 does not vary with Z. Yeah, I'm sorry, the word varies is probably wrong. It's allowed to, it's fitted. Omega 0 is fitted as a parameter, not set equal to -1. But other things being the same. And you don't invoke any time. And so in fact, this is like a constant model, constant background energy model, but not exactly at -1, not at W equal to -1. So if you do that, then here, the things that you vary are that W0, the 0 is missing here, but the W0 parameter and the omega matter that could be varying in that 30% range. And there are this set of choices which don't place omega, the central value of W0 at -1, but somewhere around that. So not inconsistent, but certainly there is a possibility that it could lie in this range. The other thing they report is in this W0, this is the W0 and the first derivative plane. And this also, so although it is consistent with the variation equal to 0, derivative equal to 0, the central value is not exactly 0. The term proportional to Z over Z plus 1 is not exactly 0. Whereas, of course, W0 primarily is -1, but it could be shifted to slightly smaller negative values. So these are the constraint on, as they call, flat W0 WA CDM. Right. Okay. So therefore, one looks out into the dark world trying to arrive at things that can be consistent with these observations. And I forgot the authors of this paper, but it's a paper that says the fabulous 5. And the 5 candidates that one could consider for putting in the dark world are the dark photon, axion-like particle, which has been given extremely extensive treatments, a dark Higgs, of course, which could be the famous Higgs portal, a neutral heavy lepton, which we all talk about as neutrino, sterile neutrino. And finally, there could be milli-charged particle, which would couple to the standard photon through a tiny coupling epsilon, the milli-charge, where there would be a fermion doing this. And in a sense, we are going to explore this fifth option. But instead of just explaining the dark matter, we are also trying to explain dark energy through it. Of course, we get dark photons as a bonus in that. Before going on, I also want to summarize what the great Xenon experiment did. This is the Xenon NT now they put. It used to be called 1T, but now they've reached some 5.6 tons of pure xenon. And so they've stopped calling it by any number, but put N. And you can see that it has, oh, I forgot to write the titles, but one is for it is for each of those dark sectors. So this is for the scalars. There are two kinds of couplings. And this is for neutrino magnetic moment. And so you can see everybody's bounds were there, but now Xenon NT has ruled out everybody. This is the axion-like particles, dark matter limits, and then finally the dark photon, dark matter limits. So they have really extensive exclusion of almost anything. There was a Xenon 1T excitement a couple of years ago, which also has been put to rest by the Xenon NT. There is now nothing. There are no discrepancies. There is no lingering hint of anything being observed. That's good news or bad news, we have to decide. So now, by way of motivating, by way of motivating where we are going, let us understand that there are all kinds of nice proposals that in a sense are quote aesthetic, in the sense that they hang together nicely, and they are not just randomly proposed one field or one field doing extremely crazy stuff all over the place. It's actually a whole sector that does certain things. And one of them is having mirror-like dark sector, a whole sector. For example, you can have SNX quarks, and well, I should not get into too much stating all this, but you actually try to visualize according to the rules of quantum field theory and its standard lore. And another sector which, for some accidental reasons, has not had interaction with ours. And if I can pick, this is somewhat old, but you can actually put constraints on the various parameters of the hidden sector if you thought in this way. One of them is, for example, the temperature that you would observe, which can be related to the delta N effective that has been, this is the relativistic degrees of freedom that could interfere with Big Bang is one thing, but they also can be detected by the CMB. That forces that temperature to be, for example, less than 0.5. Yeah, because this together is constrained, etc. So, and this one is log of, yeah, this is some hidden sector alpha and hidden sector Higgs and so on, and constraints coming from various conditions. I will not go into detail, but I just want to flash this as saying that there are systematic studies that actually think of a whole sector that would cogently explain the puzzles rather than just taking one-off particle. So the thing that we are going to look at is the possibility that extended objects serve as dark energy. Okay, so we will now focus more on dark energy and the fact that it is not necessarily space homogeneous in the space as some jelly lying through the space, but actually some objects, but which are extended and relativistic objects spread through the space. And I was not the one. I started working on this around 2005, and Kapusta's paper also came around that time. But this has been thought of by several people, and they give it different names. I now forget as some stuff that is just space filling, but need not be particles, but it is certainly extended. That is very crucial, as I will explain. And Utpal also has recently a model of dark energy using extended objects. So why are extended objects interesting? And the answer is that they have a strange equation of state. The point is that if you have, say, cosmic strings, which are one-dimensional objects, and if you pull them apart, of course, the energy stored in a co-moving volume would reduce as the cube of the volume. But because the volume expanded, it would now include more length of the string. More length of the string would be included as it expands. So while two strings get pulled apart and their total number included would go down as a cube, something proportional to A would come back in. As a result, the string scale as 1 over A squared, string energy density. And if you take domain walls, this is a very poor way. I mean, think of this as looking down into the room. But if you have domain walls, then things proportional to entire area come into the co-moving volume. So actually the density of extended structure of domain walls goes as 1 over A. And these are very interesting points, because if you now look at the possibility that you have space filling stuff all over the space, then you will roughly include as much stuff as the separation between them increased. As a result, you would find that its energy doesn't deplete at all. It looks like a constant. But it has to be entangled and mutually tied together so that it doesn't get pulled apart. We already know example of this because galaxies are not fluffing up with expansion of space. Galaxies just get pulled apart. If there are internal stresses that hold an object together, it's not going to get pulled apart. So that this kind of stuff, whatever it is, if it is tied together closely, and if it is on a scale much smaller than the scale of the horizon, it's just going to look like a constant. So the bottom line is it is not necessary to have any exceptional substance to achieve dark energy. We already know in relativistic quantum field theory that there are extended objects that can exist. So what you need is stuff that is confined by internal stresses, it is space filling, and it is homogeneous over cosmic scales. I have tried to list pros and cons. I shouldn't spend too much time, but everyone seems to think that if you have domain walls, then the W value is minus 2/3. This is true only if the domain walls are being pulled apart. They are scaling. But if the domain walls are really tied together, then eventually they will begin to look like a cosmological constant. So now we come to our, yes.
So we know monopoles, strings, domain walls. What's this 3-dimension? This thing that's filling up, which has 3 dimensions.
So it could be just domain walls, because strings don't get so knotted that they can't get pulled apart, or junctions. And monopoles, of course, are just like matter. So it is domain walls whose junctions and the sides you can't break, they would begin to fill up. But they might be crumbling in the sense that sometimes there are holes in the wall. So they may not be exactly a solid, but yeah, you would need an interconnected network of domain walls.
That's the model for.
That is the model we are trying to give. So what I'm going to do is try to propose that you have a relativistic substance, a relativistic fermion gas, which enters into collective ferromagnetism. Why did I think of ferromagnetism? Well, because of domain walls. Domain wall, remember? So trying to see if this very, very thin gas, remember there are about 440 CMB photons knocking per cc. It's an extremely rare medium. And this may be 1,000, it may be a million, but it's compared to Avogadro number, really, really, really rare medium. And can it collaboratively form ferromagnetic state in a gaseous state? It's not going to, there is no lattice to bind to. What we do expect is that there will be oppositely charged heavier particles which will keep the medium neutral. But it is this light particles, just like electrons, which may collaboratively enter into a ferromagnetic state. So actually, you will be not surprised that Bloch considered it the first thing after quantum mechanics came in, whether inside an electronic band, whether electrons can align themselves to go into a ferromagnetic state. And there is some history written here and which we will see. But why would spins align? The point is that the aligned state pushes them apart due to Pauli exclusion principle and thus reducing repulsive energy. So if there is any effective repulsive energy, then the system tries to settle in a state where it is actually the spins Pauli exclude each other so that they remain far apart. That is the kind of inverted logic. But I should tell you that till date, nobody has a quantitative calculation of any of the ferromagnetic states. I shouldn't say any, but most of them, ab initio. It's actually like a QCD problem of condensed matter physics. Nobody has a full explanation of this, ab initio calculations. They all get qualitatively correct answers and they all can, by starting off from some ground point, they can explain the rest, but not everything. Okay. So here we have our so-called Magneto hypothesis. We call it Magneto because they are very light, but their dominant feature is their huge magnetic moment. So if it's a Dirac particle, the magnetic moment is charge divided by mc. And if the m is tiny and E is in the usual range, then you have huge magnetic moments. Also, the very tiny mass makes them very large Compton wavelengths so that they can enter into a collective state. They actually can form a degenerate gas. Okay, I don't want to read all this. So many body, yeah, so there is exchange energy. And so what we are going to do is borrow the philosophy of old Landau liquid model, which basically just says if I have a gas of electrons, which are all interacting, of course, you have to have positive ions embedded so that the whole thing is neutral. Well, how much can it differ from the non-interacting system? Not very much, right? Because so aside from tuning some parameters, putting effective mass, effective other things, nothing else changes. The charge you cannot change because of gauge invariance. So this basically is the model we will also use. It was actually worked out in great detail by Baim and Chin and the other authors that we will come to, Rajagopal's group. What is needed is a calculation of finite density and finite spin. So in condensed matter physics, this is called density functional theory. In particle physics language, the density functional is a function. So density functional is a functional which is not depending on the wave functions, but directly on the density psi dagger psi. But this is exactly what you would do if you were calculating effective potential of fermion gas, because the only observable would be psi bar psi or psi dagger psi. And psi dagger, or you can have vectorial observables, psi bar gamma mu psi, and the spin observables. So it is actually calculation of the effective potential of QED with keeping all the parameters free, the charge density and the spin. So that is what it requires, doing essentially two-loop calculations. So these are diagrams, but they're forward scattering. So the momenta are actually equal. There is no momentum transfer. They are in the limit of zero momentum transfer. So this is how the calculations are done in condensed matter physics. And it gives rise to, it's effectively a two-loop effective action calculation. And it does require a density dependent and spin dependent Feynman propagator, which was worked out by the Rajagopal group. It looks very pretty, as you can see here. You have to also invoke a relativistic way of stating what the spin is. We will not go into the detail, but the point is that the parameter is the Fermi momentum, such that Fermi momentum cube is equal to the number density. And because in anticipation of the fact that this may give us, we are going to calculate it as a function of spin imbalance, we introduce a parameter zeta such that upspin Fermi energy and downspin Fermi energy actually get split. This is actually standard picture of ferromagnetism with this parameter. And so there is a 1 plus zeta, 1 minus zeta, and the number densities will just add up to give the total number, n up and n down, but they're different. So this is how net spin would arise. And the effective potential has this nice look where the theta parameter is defined like this. It is sinh inverse of the PF over M parameter. M is the mass of the fermion. So PF over M, I also write as beta. Somehow the font set I have beta doesn't have a stick below, so please bear with me. So this is how the effective potential looks like. And actually, truly it is energy per unit for volume. Exactly as you would do in quantum field theory, because they got a mass to the 4 in front. So alpha is the fine structure constant and mass to the 4 in front, everything is dimensionless. We studied this effective potential in great detail and tried to see if there were any possibility of having non-zero magnetic moment if the effective potential minimizes for non-zero value of the spin. And one finds that yes, zeta equal to 1 is also a possible minimum, local minimum. This is variation as you vary the beta parameter, that is the number density effectively. You can even go have it more favored than the net spin 0. And this is again a study now varying the fine structure constant alpha. Of course, this is a large fine structure constant, but so long as it's in perturbative regime, it doesn't matter. Okay, and so we have this phase diagram where for beta value, that is the PF over the mass value in this along this axis and the fine structure constant along this axis. Unfortunately, we should have actually focused on this because you do want fairly small alpha for everything to work well. We call this medium pi, plasma, which is asymmetric, abelian, and idealized. Idealized in the sense that I explained, it's the Landau liquid. And it has nothing, no other things. And so we get pi in the sky. And it is neutral due to heavy ionic background. What this means is that the screen Coulomb potential that the electrons feel is actually shorter range than the magnetic dipole repulsion it causes mutually. And this is why it enters the ferromagnetic state. Okay. So what do we have? Yeah. So at this point, I must admit that there is, one needs to study this more in the sense that, so we have 3 parameters, the fine structure constant, the magneto mass, and the number density, the cosmic abundance that is of these magnetos, which we call N. What we need to check is that the pressure has to be computed as rho d rho by dn minus rho, and then check what the W parameter we get. But that W is not going to be the cosmic W. That just is the local gas, which will be tied up in the domains that give rise to our domain walls. So this is an ongoing project. And here are some representative energy densities. You can have range from billions to 10 to the minus 5, depending on the fine structure constant, but it is in m to the 4 units. Okay, the mass, rest mass of the magneto. Now let us consider a hidden sector in which there is also an opposite charge partner Y, with My much heavier than just like proton and electron. You will see how I'm led to almost the mirror world in trying to think of this. So then what we first do is set for neutrality, this heavy ions Y have to be same as number densities have to be same. But now they are trapped because if the magnetos are leaking away, then the heavy particles will, but you want them to all be tied together as a medium. So it is the density of the heavy particles that will match the dark energy density. And we also parameterize the abundance with a parameter, I'm sorry, N and eta don't look very different, but this is eta Y, the abundance of the Y parameter, Y particle, with respect to the photon abundance. So at present, the photon abundance is 10 to the, I've expressed everything in EV units. So if you do this, then you get a constraint on the mass of the magneto, which is in terms of this abundance parameter eta, which could be anywhere 1000 to something, and this is the beta parameter, which roughly is 0.1. So it is certainly in the milli-eV range. And here we have tried to plot together, putting the constraints together, what the mass of the heavy particle will range over and mass of the magneto will range over as you vary this abundance parameter with respect to photons. And so you might take a pick at something like this, millions, micro EV, then you will get a something in, keV, 10 keV kind of particles. Then we can also solve the concordant puzzle by assuming that there are heavier brothers of these, but that photon temperature is such that it keeps the lightest pair ionized, because the binding energy goes as alpha square times m. So the lightest m pair would remain ionized, but the heavier masses would actually form hydrogens, and they could come together to be a combined medium and act as dark matter. In fact, some of the heavier ones also could get ionized and be fraction of what neutralizes the magneto gas. So the heavy flavors then could account for dark matter forming dark atoms, which have the first graph that I showed from Klein's Lesuche lectures actually is constraints on dark atoms. And so one requires that the second generation ones, their masses times their number density, provides dark matter, let us say, which is about the same range. But also these two must be at least keV to serve as dark matter, because otherwise they would be too light. And if you do that, then you get again a constraint on the abundance of these. This is not very, this is very reasonable in terms of keV. There would be some fraction of photons today. Okay, what is more interesting is that we get origin of cosmic magnetic fields, because these are after all magnetized domains, they are spin polarized. And all you need is a large number of such domains over which, of course, net magnetic field would be 0, but there would be an RMS field left over, something that trickles through the whole thing, proportional to the number of domains you thread through. So the RMS field over n domains would go as 1 over square root n. And if you do this, and there would be some residual delta B bar, RMS delta B. So by assuming a parameter psi, a mixing with standard electromagnetism, this is F mu nu x and this is F mu nu. Then we can put a constraint on what the delta B seed can be. Well, so it's the other way around we do that. We ask for minimal seed required is 10 to the minus 30 Tesla. So if we set this, then we get an estimate of the size of the domains L. And this is some picture of the size of the domains versus the mass of magneto again. This is, here the magneto masses are larger, because otherwise this becomes 12. So you can get estimates of this kind. And this is in the solar system range. The right, the domains would be solar system. They could be, I mean, here numbers really, we are actually talking in the exponent, so could be much larger or much smaller. Okay, so I think I've presented the essential scenario, and we do need to understand the nature of phase transition, that so it would reflect on the dark ages that are being talked about. The ferromagnetic state would come into existence sometimes during the dark ages or during the early dawn. That would be very interesting because they would dump entropy into the universe. And one has to study the fluctuations and stability of this medium. And if it comes into existence, then the rate at which it can degrade, because as the number density goes down, you might move away from the ferromagnetic state. For all we know, within the last z equal to 1, it has already melted away and gone away. So all these Pantheon exercises which try to fit WA should find that depleting dark energy. Well, so yeah, it should be able to predict omega 0 and omega 1. And then there is the question of compatibility, connection to standard model, and compatible, so that it is compatible with this giant killer experiment that we have. Good. So then there remains question of observables. For some time I was excited because they said there was some milli charge, but Saras 3 has now killed it. So maybe it is millier than milli, so whatever. So we have to search. I invite you to think about the possibilities within this scenario. Thank you.
Okay, thank you.